Hello everyone. So we will be solving the maximum area of two non-overlapping uh, submatrices. Before we start, here's a beautiful quote that whether you think you can or you think you can't, you are always right. What does this mean? That if you believe that you can solve something, then definitely you will be able to do it. If in your mind it's already done that, hey, I can't do it, then you won't be able to do it, right? So it's most of the time it's about the mentality that you have in yourself. So when if you have a choice to think in a positive way, do think in the positive way to ensure that you can achieve your dreams, right? So let's read the problem statement. It's a beautiful problem. It's a problem which we will be solving using binary search and DP. If you have like if you are afraid of DP or binary search, first of all, don't be afraid of DP, right? Because uh, it's intuitive. When you get once you are used to it now, it becomes very intuitive that hey, DP will be used, and how it will be used, it will be also understandable at a point, right? So you just need to hold with it for some times, right? You can't run away from it for a long time, right? Enough again for this one. Let's read the problem statement. You are given a 2D integer matrices which is called mat and a size of m cross n, where matrices of r commas rc, if it's equal to 1, it means that the cell at row and column is usable. If it's 0, that means it's not usable, right? Your task is to find two submatrices that satisfy the following conditions. So any two submatrices you need to find, right? Both submatrices must be a square of same side length k, and the two matrices must not share any common cell, right? Each submatrices can only cover the cells which have value 1, right? We need to return the maximum possible area of the two following squares, right? Now let's see this problem statement. Let's see, this is the test case, first test case, right? If we look at this test case, what do we understand? The first submatrix will be this one, right? See, this sub part is the uh, submatrices, which will be the first one of size 2 cross 2, and similarly this is a 2 cross 2 submatrices, right? See, both contains all the ones, and they don't share any common cell. Common cell means if this one was a part of this submatrices, that would be a violation of the rule, right? If you look at this one, the only possible submatrices of size 1 is possible, right? And in this case there is no two submatrices are not possible. This is only a single submatrices of size 1 cross 1, right? So if we look at the time constraints, the time constraints given is n and m can be till 500, right? Now let me give you a brief introduction of how can we solve this, right? Yes, give me a second. Yep. So my first take on the problem solution would be, hey, this problem is monotonous. You will say, how is it monotonous, right? Really sorry for the spelling. Yeah, so let's say if I'm saying, hey, can you find a matrix of size 3 cross 3? If you say yes, right, then I can say might be you might find a matrix of size 4 cross 4. You might find, right? I don't guarantee it, but you might find, right? But if I say, hey, can you find a matrix of 2 cross 2? Then you will definitely say, hey, yes, I will find it, right? Because if I can find a 3 cross 3, if you look at 3 cross 3, how does 3 cross 3 looks like? It looks like something like this, 3 cross 3 matrix, which contains all the ones, right? If you can find a 3 cross 3, then inside it belongs 2 cross 2. Yes or no, right? If you can find 2 cross 2, inside that you can find 1 cross 1, right? So, sorry for that. So if you look at it, don't you find monotonicity? How? Because I'm saying, let's say if I can find a submatrix of 4, let's say if I say I can't find a submatrix of 4, right, of length 4, right, I can't find a submatrix of length 4, right, then it is guaranteed that I won't be able to find a submatrix of length 5 as well. Yes or no? Because if you can't find a 4 length, how will you be able to find a length of 5, right? So this gives you a brief hint or a starting point that hey, you should use a binary search. Yes or no? So how we'll be using binary search? We will say, hey, can we find that, right? What will my binary search be? My binary search will say, hey, can we find uh, two submatrices, two submatrices of length, let's call it sz, right? If we say yes, then we will update our binary search. How will we say? Let's say if we are standing at, if this was our mid, right? If I say yes at this point, then everything on my left is also a yes, right? Now we need to find on the right side, right? So what I will say, I will say, hey, update my start to mid plus one, yes or no? I hope you know a bit of binary search, so this will make sure that you understand it, right? So let's say, if even if you don't, if this says yes, then my starting point or my search space starts from this place, right? My start comes to this place, my end comes to this place, right? So start and end becomes this. Now we will search mid in this place. If this says no, then my end will come to this point, right? My search space becomes smaller, right? So binary search will help us find the length of the submatrix, right? Sz, which we are calling as of now, right? But how will we find that the matrix contains that size or not, right? So when I first thought of the problem, I thought, why not go with greedy solution of just finding a size sz, right? But that will fail, right? And why does that fail? Because see, you do, let's say if you had a matrix, right? Won't like draw the full matrix here. Let's say you're starting at this place, right? And you picked this submatrix as of now. Let's say not this one. Let's say, give me a second. Yeah. So let's say you picked this one, right? After you pick this submatrix, right? You won't be able to find a submatrix, because greedy means what? Greedy means as soon as you find the submatrix, first submatrix, you have it, right? You will say, hey, this is a submatrix, I want to have it, right? You will have a, let's say size was 3. But when you do so now, you left no submatrix of size 2 cross 3 to be available, right? Instead what else can we do was, let's say if this was possible, let's say there was one more column, right? Just for understanding, right? There was one more column, right? Now instead, let's say if you had picked this submatrices instead, and let's say this was also a valid one, then that would be a better choice for us, right? I don't have a, I can find a proper example for this where the greedy solution will fail, but I hope you understand that greedy will pick the first element, first submatrices, leaving us with no other choice of finding another submatrices. Instead, let's say if this was the submatrix which you greedily picked, instead if you could push this one by just a single block and find a submatrix with this place and another submatrix like this, then that would be better for finding two submatrices, because just because you picked this submatrix, you block this path as well, right? So that is the reason greedy solution fails in this, right? So there comes the DP approach, right? Now, what is the DP approach? The DP approach will store a certain value. Now, what's that value? Let me first write it. So DP of ij will store that, hey, what is the maximum size of square that ends on I comma j, right? I have a visualizer for this as well, where we will see how DP will be storing values and all of those things, right? But as of now, you can understand, hey, DP of ij will store the maximum size of square that ends off on ij. What does this mean? Let's say I'm standing at this square, right? Now this square will, this point rather, this point has a 1 on this place, 1 on this place, 1 on this place, 1 on this place, right? Let's say this was only the block, right? Now this will, this is a square of length 1, so this will store 1 in this. DP of ij will store 1, right? This will store DP of ij as 1, this will store as DP of ij of 1 only, right? What will this store? This will say, hey, what is the minimum out of the 3 possible ways to make a square, right? When you stand at a point, you can go top left, you can go top, you can go left, right? These are the 3 points where you will be expanding to form a square, yes or no? So when you are doing so, you will ask, hey, what is the minimum value? Why minimum value? Why not maximum value? Because see, if this says, hey, I don't have a value, let's say it was a 0, right? Then you can't a form of square of 2 cross 2, yes or no? But because its value is 1, right, now you can say that, okay, this has a value of 1, this has a value of 1, this has a value of 1, all has a value of 1, so it will contribute a size of 1 extra to me, and I will have a size 1, right, because this alone can form a size of 1 cross 1. Yes, so this will store 1 plus 1, which becomes 2, right? So see, this is a 2 cross 2 block as well, right? So I will have a visualizer. Just hold on for a minute. I will show you how the visualizer or the clear explanation of how the DP table would exactly look like. But I hope till this point we are clear that what does DP actually store, right? So how will my DP state look like? Or rather, let me, because I also prefer using a recursive way. So what we will say, hey, solve function will do nothing, but it will find int left, right? It will find left value. How will it find? It will say, hey, go solve of I comma j minus 1, right? Int top value, how will the top value come? Top value will come with, if you are standing at this place, going left means j minus 1, going top means going I minus 1 comma j, right? And going top left will be I minus 1 j minus 1, yes or no? So if you want to go to top, you will say, hey, I minus 1 comma j, yes or no? If you want to go top left, how will you go? Top left will be solve of I minus 1 j minus 1, right? So if these three values are found, if you find these three values which will be found by your solve function, then you can say, hey, dp of I comma j, if it's 1, only then it is possible, right? Because else you won't be storing any values, right? Because if the value is 0, right, I hope I have not missed this part of making you explain that if the value is 0, then you don't care, right? You don't care about that, right? So dp of I comma j will be nothing but minimum of left comma top left, right? So these three values will be stored in the dp of I comma j, and plus 1 because 1 plus this. Why plus 1? Because see, if this block is already there, right, and you are finding all the blocks which were 1, so what did we do? We simply asked them. These will return a value of 1 from all the sides because minimum is 1, and this itself will contribute a block of 1 cross 1, right? This is contributing a block of 1 cross 1, right? So ultimately the block becomes of size 2 cross 2, yes or no? So I hope the dp part, or how the dp part code would look like, is clear to you. Now let's look at the visualizer which I was talking about. Give me a second. Yes. Yep. So this is how my table would look like, right? If you look at it, see, this is a 5 cross 5 grid, right? Now let's try to say if we can find a 2 cross 2 grid or not, right? It is very interesting if you look at it, right? Let's say if this block is already 0, right? Let me mark it as 1. Now see, the dp value stored is 1, right? Let's say if this was also a 1, right, and let's say this is also a 1 and this is also a 1, now you see the dp value stored at this place will be 2, yes or no? Right? Why it is 2? Because see, the block has a value 2 cross 2 grid, right? Let's do it at somewhere else. Let's say this was 1, right? Let's say if this is also a 1, right? Let's say if this was also a 1, see, still its value is not 2, right? But let's say if this was also 1, right? Now this value is 2, right? How? Top left, if you see the value, we can see as well. Top is giving you 1, left is giving you 1, top left is also giving you a 1. So ultimately its value becomes 2, yes or no? So isn't it interesting? So this is the dp part, right? Or how the dp would look like. Let's create a 3 cross 3 as well. So how will this value change? If you bring all these three values to 3 cross 3, means all of them becomes a 1 as well. So let's create a 1 here, 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 and 1. If we click 1 at this place, this value should become a 3, right? You can see now this value has become a 3. These value has also been updated. This has become a 2 cross 2 grid. How this is a 2 cross 2 grid? I want you to write and think of how this, I think the formula is already written here, so that won't be a good one. But you need to think of how this became a 2, which were the blocks which have identified. I hope this is very obvious, because this block and this block are contributing to a 2x2 grid, right? So this was a DP visualizer. If you look now, these values is 3, right? So that was the DP visualizer. Let's move on to the last part of understanding of how we will use this DP table, right? Great. All right, so this is how our table looks like, right? We saw the DP visualizer thing, and this is how my table would look like, right? All these contains a 0, right? So I'm not writing all of them. So now how will our binary search and DP work together, right? So now let's say my binary search said, hey, if my size is 2, can you find a 2x2 grid in this, right? That what binary search will ask. So what you will say, hey, let me ask my DP table. I have created the DP table for once. Let me go in and ask in that DP that if 2x2 is available or not, right? So how will we find that? See, whenever we go inside the DP table, this 2 represents that 2x2 grid is available, right? This represents 2x2 grid is available. This represents 2x2 grid is available, right? So whenever you go in the DP table, you will have 4 things with you. You will have a max row, you will have a min row, right? You will have a max column, and you will have a min column, right? Now what does this mean? When you want to find a size of 2, you will have these max row, min row, and all of those things, and you will just traverse on the DP table. And if you get a value, if you get a value which is greater than equal to size, right, then what you can say, you will say, hey, I can have it, right? That is, let's say if you get a 3 value, that means 2 value is also somewhere in that DP, right? So you will update your max row and all those values, max row, min row, and all those 4 things accordingly, right? Let's do a dry run to understand. See, we had a size of 2, right? You went to this, you went to this, you went to this, you went to this, and you will say, hey, I found it. So let's mark them as well. 2 3 4 0 1 2 3 4, right? So when you come to this 2, right, you will say, hey, I found it. So max row will be, row is 1, min row is also 1, which is because you have found this for the first time, right? Max column is 1 and min column is 1, right? Now you will go on traversing on all those elements again you will find this, right? Now max row becomes 3, right? So max row updates to 3. Min row means minimum row. We already had minimum row at 1, right? So we don't need to have it again, right? Then we have max column. Max column will be 3, right? So you will say max column updates to 3. Min column is 1, so you won't update it because you are storing the minimum column where you find that size value or the value was 2, right? So this is now how the max row and min row, really sorry, let me see, yeah, max row and min row will look like, right? So max row will be 3, min row will be 1, max column will be 3, and min column will be 3, right? 1, right? Now what can we infer from this? What information are we trying to extract? So I will say, hey, if my max row minus min row, it is if it's greater than equal to size, right? Or if my min column minus sorry, max column minus min column is greater than equal to size, then I will return a true. Why will you return a true? See, in this case it is 3 minus 1, which is 2, which is already greater than equal to size, right? So this should return a true. Why should it return a true? See, this has a size of 2 cross 2, and there's also a matrix which has a size of 2 cross 2. Even though when you go on this 3 value now, this max row will be updated to 4 rather, and max column will also be updated to 4, right? So again the value is 3, means the difference, max row minus min row becomes 3, which is also greater than size, so no worries for that. So that means you can find a 2 cross 2 grid at 2 different places. That is what max row minus min row suggests. Because if my minimum row where we can find the value was this place, and the maximum row, let's say, and in this case let's assume it as of now was this place, so if we can go to left and still be bifurcated by a line, or there is no common cell, then we can say, okay, we found a value which is correct. right? Let's quickly look at a case where the value won't be correct. Let's say uh, if we had 1 1 1 1 all the one, right? So this value would be 3, right? This value would be 2, uh, this value would be 1, this value would be 2, this value would be 1, right? So in this case, let's say if your max row was this one, right? You wanted to find a 2 cross 2 grid, right? So let's say you wanted to find a 2 cross 2 grid. Let's quickly understand it, how max row and min row will work. 2 cross 2 grid. So max min row, where you find the first two, will be this place. Let's call it 1 comma 1, not 1 comma, it's actually 1 comma 1. And max row will be this one, because 3 is also greater than 2, so max row becomes 2, right? Min column becomes 1, because this is the first place where you find 2, and max column becomes 3 2, right? So in this case, if you do a 2 minus 1, it becomes 1, which is less than equal to 2. So that is the reason you can't find a 2 cross 2 grid in this case, right? Can you find a 2 cross 2 grid which is not overlapping? No, you can't find. And how did we do that? We did it with max row minus min row, which is 2 minus 1 and 2 minus 1. Both values are less than size, right? So that is the reason it will return a false, right? So I hope the problem statement or the clear explanation was, the explanation was almost clear to you, right? If you have any doubt, you can ask in the comments as well. So let's quickly look into the code part of it, right? A beautiful problem, right? Even if you are not able to solve it, it is a beautiful problem to go again and think of it, right? So let's see at the coding part. We will first create a DP, right? And then we will solve a DP vector for it, right? So solve DP. So what are we doing in this DP? We are simply saying if I is less than equal to j, and all those same things which we have discussed earlier, right? So if you know a bit of DP, if you don't know DP, you do let me know in the comments. I will create a separate video on how do we solve DP problems. But in this, I think explanation explaining exactly each line of DP would be a bit difficult. So, but still, let's say this is the memorization part, right? If you haven't stored the value of DP, you will return that value. If the value is already a 0, right, then you need to return nothing. You can say that dp of ij is 0. You have a left value, you will have a top left value, you will have a top value. We have shown that how will we be finding those values. After finding that value, we can say dp of ij will be minimum of those values plus 1, right? Why a plus 1? Because this value has already a 1 in it, right? Great. So this is the dp table. Then we move to the binary search, right? Start becomes from 1, end goes till n comma minimum of n comma m, and we start the binary search. So binary search finds the mid, start plus n by 2. We will find call a solve function in is valid function. Is valid function will check if that mid value is available in our dp or not, right? If it's available, we can say answer equal to mid, and you do a start equal to mid plus 1, right? Else you say end equal to mid minus 1, and you will return answer into answer. Why? Because if a 2 cross 2 grid is available, you need to return a size of 4, right? That is what the problem asks you. If you had a size of 2, you need to return a 4, right? In this case, if you look, a size of 2 is available, so you return a 4, right? So let's really sorry, give me a second or so. Yeah, let's quickly look into the isValid function. So isValid function will have max row, min call, and max column. Will traverse on 0 to n all the elements of uh, the matrix which is given to us. And if my dp of ij is greater than equal to sz is being passed as a mid function, right? So we have discussed it already, why, what is sz and all of those things, right? So we'll update the max row as maximum, min row as minimum, max call as maximum, and min call as minimum, right? And we will simply check if max row minus min row is greater than equal to size, or if my max column minus min column is greater than equal to size, then we will return a true, else we will return a false. So that is it for the video. One more thing, what is the time complexity? If you want to understand, think of it, what can be the time complexity, because we are creating a dp, right? So dp table would take a time complexity of give me a second, yeah, it will take a time complexity of big of n square, right? Or rather we can write it as big of n into m, right? And then after that, we are doing a binary search. So binary search takes big of log n, and after that you are traversing on that db table, so it becomes big of n into m. So ultimately it becomes big O of nm log of nm, right? So this is the time complexity of the problem. I hope the explanation was clear to you. The visualizer thing was also cool. If it was, do give a like and comments in the right if you understood in the comments, and do subscribe as well. It motivates a lot. Thanks for watching. If you have any doubt, you can ask in the comments as well. Thanks.